tuning in. We're beginning soon, but in the meantime, go ahead and start the warm-up activity. Just designing some kind of robot that would help you solve a problem in your life. It doesn't have to be a big problem. It can be a very small problem if you'd like. But the key is to find something specific that you think is better done when you don't have to do it. Also, I'd encourage you to write it down. Try to get a good detail in there if you'd like. Sketch it if that helps you. I'll be getting back to that later, so it's good. It's good to have that in advance. Uh, can you design a dishwasher? You can. Later on, we're going to talk a bit more about what is and isn't a robot and does it even matter. So we'll be talking about dishwashers in particular. Right? We are filling up. As you come in, just go ahead, pull out a piece of paper, type something on your computer for the warm-up activity. You can write it out or sketch it out. Just design some kind of robot that would help you solve a problem in your life. Kellyanne, I must imagine this was an interesting experience with only the one screen, because I'm sitting here with three, and it's
It was a lot. I Our friends from Suffolk Construction helped helped
right.
me along with that. But yes, it's good to have extra screens. It's a learning process for all of us.
Mm-hmm. For everyone tuning in, we're starting in about a minute, but the first bit of the first bit of the webinar will be the warm up activity. So go ahead, pull out a piece of paper, uh, pull out a sketchbook, whatever helps you in your creative process to design some kind of robot that would help you solve a problem in your life. So far, we have a laundry folding robot. We have a trash bringing outing robot. That's how you say that. Don't question it. We have some kind of robotic dishwasher. What are you saying, Kellyanne?
I was saying it's your invention. You can name it whatever you want.
Exactly. Drew a robot that did my math homework. That that is a robot that will not help you. In fact, you need to do your math homework. It's very important for robotics. That said, if you could make a robot that did your math homework, honestly, you wouldn't need to do your math homework anymore at that point. There's another one for annoying homework. Look at that. Again, if you can make a robot that can do your homework, you're going places. pick out clothes for the day. That's an interesting one. I want to bring up some dated movie references. It feels weird saying something's dated when you're in your 20s, but I know they're dated.
I talked about the Fresh Prince of Bel-Air yesterday.
That'll date you. that predates me. So robot that can play 1v1 basketball against you. That reminds me of the robotic soccer tournaments that have popped up over time. I know they have them every once in a while. That would be a very good one. And we'll get into that one in particular, actually. So if I forget, remind me that I said I was going to bring up the basketball one. A robot that can carry you on the couch. So you're lazy. So you want the robot to like carry, so you want to just be sitting on the couch and the robot just picks you up and moves you around your house? Because if that's the case, I want you to consider the difficulty of moving a couch through doors and how you design a robot to get around that. Robot that picks up litter. A robot that can build other robots. Robot that can build other robots. So for one, we'll talk about that as well, because even in the building of robots, having robots is very helpful. A whole bunch of people are coming in. We are getting started now. So the first thing is to do the warm-up activity, which is to design a robot that would help you solve a problem in your life. You can grab a piece of paper or write on a computer, sketch something out, whatever helps your creative process. Just design something that's interesting, something that you've always felt like you've wanted, with absolutely no limits here. Robot to tell me to eat left Twix or right Twix. You don't need a robot for that. Both. You eat both Twix. Or you know what? Share one with a friend. Eat both. Robot that makes me food. There are some robotic restaurants. I know there's one in Boston, somewhere near South Station. So that is a very good idea. Robot that can organize their art supplies. So for something specific like that, for something like art supplies, honestly, a robot that can organize anything is top tier. Robot that destroys the world. I'm gonna veto that one. We want no robots destroying worlds here. I like the world. Robot to give me free frozen yogurt and has all toppings. Now that just sounds like you're stealing. Where are you getting this frozen yogurt from? So I can see everyone's having a lot of fun making their robots, but I'm going to add one little thing while you're designing this, and that's try to figure out exactly how the robot does the thing you want it to do, because that's the important part of the design process, right? You want to make sure that it's not only the idea that matters, but how will it do that? How are you designing it so that it can do what you want? Robot that can dance. So is that robot to help you dance, or is it just because you want a dancing robot? Robot that can buy me a Nintendo Switch and Animal Crossing. Now, remember when I said you want to figure out how the robot is going to do what you want. So it sounds to me like you want a robot that can make money, right? So how can you design a robot that can make you money so you can buy Nintendo Switch and Animal Crossing? Oh, and then a robot that makes legit money. Yeah, that's don't print money. That's illegal. Don't do that. Made an EV3 robot that sorts out trash. That's Lego, right? Lego EV? I think so. That's super cool. That's really cool. Robot that can change weather, get food from the kitchen. For anyone just tuning in, we're doing the warm up activity where we are designing robots that can help us solve problems in our daily life. Grab a sketchbook, notepad, whatever you want to design it. Try to think not just what you want, but how are you going to design it to do the things you want to do. Okay. Right, I'm going to give it another 2 minutes, and then we're going to start talking about robots. See, another robot destroying the world. None of that here. In fact, that is exactly the opposite of what we're trying to do with the end project of this. Robot that can suck up water for floods, put sesame on bread. Robot that can make good for free. I'm assuming you meant food. Built-in tools and knowledge to relieve stress. Health checker sanitizer robot, that would be helpful post our situation right now. It's always good when you take a situation that exists and you see that this was something which could have been prevented or something which we can improve on in the future. And then that's when you can design something that truly will make a big difference. All right. Okay. So it looks like we have about 70 people. I'm guessing that's about what we're going to hit. So I will begin my thing. So I hope you guys enjoyed coming up with random robots. Some final favorites of mine. We have a robot that eats houses, which, while it sounds like a joke, demolition very important. And then we have another. Can it be a robot that destroys the world? Okay, I'm gonna continue on before you guys continue destroying the world. So welcome to the future construction. This is the robotics side of that. So I'm from MassRobotics, and we house a bunch of robotic startups that do similar things to what you guys were brainstorming before, which is they make robots and try to automate things, and we give them the tools to actually make their dreams a reality. So it looks like you guys are already pretty well versed in this, but you should see a Q&A and raise hand button at the bottom of the screen, I believe. Chat has been disabled. We're not using chat, but you can talk to me using the Q&A. So I'll prompt you whenever we're doing that kind of section. Very quickly, everyone press the raise hand button so I know you guys all know that right there. Look at that. Very quick. All right. Awesome. Looks like you guys are all on top of it. Right. So first question, obviously, is what is robotics? I know we all have some kind of idea of what it is, but we want to get more specific now. So robotics as a field is all about the design of the robot, which is what we're doing before. It's the what is the purpose of the robot, and then what are the things that we need to put to give this robot so it can do the things that it needs to do. You have the engineering side. So now once you have the design, then you have to actually engineer the thing. This is when you start putting it together. This is when you have to use skills you've learned in school, your math, your science, your physics, right? To figure out how exactly can we make the design a real thing. So once you have the design, you've engineered it, right? Someone actually has to operate a lot of robots. So some robots work on their own and others work in tandem with humans. So the ones that work with people actually have people working alongside them in order to operate it. And also the application, so installation and such, all has to be done by someone. So these are all things within the fields of robotics, right, of robotics and automated systems. Um, I won't get too much into the difference between a robot and an automated system, but just know that there is some nuance there. Right, so what is a robot? A robot is anything that can sense the world around it, takes that data, computes it, and then actuates it in some way. So the term actuates, what we use in robotics, really it just means moving things. So that's something like an arm, right? That's actuation. In a car, a wheel, right? Something which actually moves. It's not just a digital computer thing. It's has to functionally move something somewhere. Otherwise, we can't quite call it a robotic system. So I want to go over some robotic systems. This one right here is the NASA Valkyrie robot. We have one in MassRobotics, and this looks a lot like what I imagine many of you think of when you think robot. We have a we have an idea when we think of robots that comes from a lot of media, and while this is broadening these days, this still is a trademark version of a robot. But even this robot, right, it has to go with the same rules that we gave for all robotics. So it has to have some way to sense the world around it. In this case, it has infrared sensors, which are a type of sensor that can sense distance by sending out two different signals, one that sends out a signal, and then one that will receive it. And using that, it allows it to figure out the distance between objects. And then this one also has cameras on its front and on its back. Important thing to notice for this is while it looks a lot like a human, it has cameras that are located in the torso area, right? And this is one of those things which, at first glance, you might think you want to put the cameras in the head, right? That's where the vision is. But we're not robots, right? We're not bound by the same laws that humans are when we design a robot. So a camera can be put wherever it's best utilized. You could put a camera on the robot's hand if that would help it serve its function. So in this case, it has one. They're called hazard cameras, in order to sense danger, right? So the compute side is the interesting part for this particular robot. So the infrared sensors, it's a little more complicated than just an infrared sensor, but the idea is it can take the data from the distances objects are from the robot and can turn those into points that can create full 3D models of spaces. So the image you see right here is one from the sensor being used in the NASA Valkyrie robot. And it can map a space as it's moving through it. So this gives it eyes, kind of like what we have. And then the actuation is the legs, the arms, the wrists, the head, right? So robot. Now this is a manufacturing robot made by Universal. And at first glance, we might think, okay, this, I can see the actuation. It has a whole bunch of joints. And you can see this actually has more joints than a human arm, right? So you have the joint at the bottom, the joint at the middle section, and then there are a whole bunch around the arm, around the hand. But even this type of robot has some types of sensors. This particular one might use a force torque sensor. Now that sounds super fancy, but all it really means is it gives the robot a sense of touch. But that a sense of touch doesn't mean anything unless you have something you want to do with it. So the compute for this one is a control box that you can see at the bottom, and it will take the data from that force torque sensor and uses it in some way based on how we program it. So an example of why we might want this kind of sensor is, say you wanted to pick up an object, right? Now, if you wanted to pick up a rock, you could use any kind of force. You could just hold it in your hand. It's not going to go anywhere. It is not going to break, right? However, if you wanted to take the same robot and you want to pick up an egg, it needs a much more delicate touch. And without the proper sensor, the same robot would just crush that egg. And that's one of those problems that is surprisingly common, even right now, to have robots that have some kind of dynamic understanding of what they're holding. So I have an exercise for you guys. I have 3 things here. One of these is an automatic door. One is a washing machine. Remember, I was going to get back to the dishwasher before? Washing machine is a similar deal, right? And then you have a desktop computer. So I want you guys to raise your hands if you think an automatic door is a robot. Looks to me like we have about half of us think an automatic door is a robot. If you say it's a robot, I want you to go in the Q&A and tell me why it's a robot. Remember to use the sensing, computing, and actuating, right, as our criteria. Right? So a lot of the answers are, it has a sensor, so it knows when someone's near it, and then it moves itself, it opens, right? And so yes, automatic doors can be classified as a robot, right? Even though we don't necessarily think of it as a robot, the fact that it has some way to sense the world around it via a sensor at the top, you see that little black thing, right? Often that's some kind of proximity sensor, or a mat at the bottom, right? That senses when someone steps near it. It uses that to sense. And then again, sensing data on its own doesn't do a whole bunch. So something in there has to compute, okay, when there's someone nearby, open the doors. And that's the actuation, right? So that qualifies under this definition as a robotic system. Now, a washing machine. Is a washing machine a robot? Raise your hand if you think so. So this one, a lot fewer people think of a washing machine as a robot. Looks like about a quarter. And so if you think it's a robot, I want you to tell me why. Okay, so this is a bit of a trick question. It's a trick question because it kind of depends on the type of washing machine you have. If you have an old type of washing machine where you told it exactly how big the load was and what temperature to put it at, right? Then it's a lot less of a robot because you've given it all the sensor data that it needs. You've told it how much is in the load. You've told it how long to go for. And you've told it what heat or what have you, right? So that wouldn't qualify as a robot. However, More modern washing machines often have load sensing, so it can now take the clothes that you've put in, and it will know how many clothes and therefore how long to actually run a load for. So again, that one depends on the type of thing, but you can see how the definition of robot itself is kind of loose, right? Um, the last one is a desktop computer. Now, this one, I will tell you in advance, is also similar to the washing machine. It kind of depends on the computer. But in this case, I pulled up a picture of this one here because it has several things, including a fan system, including a water cooling block that does have a pump in it, right? So I want you guys to tell me using Q&A if you think a computer is a robot and why. So I got a couple really good answers right off the bat, right? The first one is if the CPU gets hot, there's something which senses that heat and then turns the fan on. And then I have another one, right, which is talking about the water cooling, which will run the pump based on the heat, same as the fans. And so, yes, in a lot of ways, a computer is a robot. However, and this is a big however, a computer itself does not do a whole bunch with a lot of that data. A lot of that data is kind of situated within the cooling system of the computer. And so while you can call it a robot, right, and it fits our loose definition of a robot, because it doesn't, those things in and of themselves aren't really primary function where, you know, using a desktop computer, opening up applications and such, they're kind of secondary systems to the computer. So we can call it a robot. We can call it not a robot. Ultimately, it doesn't matter a whole bunch because robots are not just about is it a robot, it's also automated systems, right? So those are the two things that fall into the robotics term. So a lot of the things in the washing machine or desktop computer, we can call robots or we can call just automated systems, right? They are two different terms that both help you understand um, what robotics is. There's one answer in here that says, but a computer doesn't move, right? Same thing with the washing machine. And I want to clarify that actuation doesn't always mean move in space, right? A fan has a moving element, same thing with the washing machine that tumbles around. So they qualify as actuating, which is why we use that term as opposed to just moving. So why use a robot, right? Why do we make these robots and design these automated systems, right? There are the 3Ds is a kind of the standard thing that people use when they think why we use a robot. So the first one is for dull tasks, tasks that no one really wants to do. So for instance, sorting trash with one of the robots you guys were talking about earlier. Washing laundry. If you've ever seen old images of people washing laundry with kind of a board and they're scrubbing against the board and then they're drying it up on clips, right? You can do it, but you'd rather something else do that, right? Dirty tasks. So things which are just a lot filthier than we want to put, filthier condition than we want to put humans in. So a lot of things like sewer inspection, for instance, right? I don't think there's anyone here that is all too keen on hopping in a sewer. Another one is anything dangerous. So those are your basic 3Ds. Danger in this case, think of a bomb robot, right? A robot that goes and tries to defuse a bomb, so we don't have to send a human to do that. we'd much prefer a robot to do that because obviously there's danger there. I like to throw in also very precise tasks. So um, there are a lot of tasks which are just far too precise for a human to do accurately consistently. So a lot of your 3D printing, for instance, right? Heavy machinery uses some type of automating system in order to make sure it's always doing things correctly. So in general, it's things we can't do, or it's things we could do, or rather not. And then there's things we can add so that people can work more efficiently, right? The example I have here is the robots they use at Amazon. So Amazon robots are a lot of fun because if you've ever seen robots that take packages around, right, or people can put a a parcel on a robot and it will fly around, that's cool. Amazon just takes it one step further, and the way their system works is they have that little orange robot at the bottom that will pick up an entire shelf of goods, and they will bring it to a person, and that person will then pull out the item that you ordered before they ship it off. So instead of it being one thing at a time, they'll just bring a whole shelf over, which I think is super cool. It is, using this understanding of robots, right? We can see there are a lot of applications for it. It hits almost every single industry in some way. So if you guys have any questions, now is a good time for that. Otherwise, this is our first small break before we get into the next portion of the talk today. I can see here, what is the most common robot we use in everyday life? Depends on your everyday life, really. If you have a self-driving car and you use that every day, right? Again, it really depends on depends on what you use every day. Some people have Roombas, the iRobot sweeping robot that goes around and sweeps everything for you. That was one of the most popular robots for getting people to understand that these are things that are not scary. These are things we all can use and have and will improve our lives. Can't people just steal the other things on the robot? So I'm assuming if you're saying like, are you talking about like with the Amazon robots, right? With the whole shelf? Because that's just within their facility, right? So they obviously have some kind of security to make sure people aren't just taking stuff. But as robots get, as we start seeing robots more and more, like in streets and such, that's exactly the kind of consideration that people have to take. There's a company that makes a little roly-poly robot that is essentially a suitcase, right? That will follow you, and security becomes a big issue with stuff like that. So it has to lock, and then obviously has to follow the right person, because if it followed the wrong person, then someone else is running off with your stuff, right? So security is always a big concern with this kind of robot. Will a fridge, a dishwasher, and a sink be classified as a robot? So that is a question that I believe you can answer yourself, right? So for instance, a sink, let's take an automated sink, right? If you have a sink in like a public restroom that can sense when your hands are under it, that technically, again, it's one of those, you can call it a robot. Is it important to call it a robot, right? It's that's why I want to separate the idea of, is it a robot versus is it robotic, right? Is it some kind of automated system? Not everything that uses automation is a robot, but that definition isn't always important. Can a virtual assistant be a robot? Virtual, no, right? So that is artificial intelligence, sure. and artificial intelligence and robotics in many ways go hand in hand. But as a purely virtual thing, it is not a robot, right? If you gave that virtual assistant a body and then allowed it to kind of move based on whatever it's trying to assist you with, then yeah, you've made the ultimate robot butler that we all want. Is mayonnaise a robot? Can robots talk? Some can. Is Amazon Alexa a robot? So that's the same thing with the virtual assistant, right? Um, in and of itself, it's not, but attached to other things, it could become one, right? Uh, virtual reality, yeah, virtual reality is not a robot. If it's not within our world, if it's not moving or actuating right somewhere in real space, not so much. Is a car robot? Again, that one depends on the type of car, but every car that's made nowadays has sensing units all over it, right? If you've ever seen cars that park themselves, that's an obvious one right there. But there's also cars that will just beep if there's something behind you, right? That's using sensors to detect that. Um, that doesn't qualify alone for a robot, but it is an interesting thought. You are not a robot, random person. I believe in you. You're a real person. Have you met any robots? If by meet you mean use or see, tons. So at MassRobotics, we have robotic arms. We have the NASA Valkyrie, right? We have robots that can kind of just go around and pick up packages and stuff like that. But like I've said today, we've all interacted with robots many times, right? So there's a someone said people try so hard to make a robot like a real person. This is something we'll get into in 2 minutes when we go into the next section. A lot of things about making robots like real people when you come to design robots. Have you made a robot? I have made many robots. How long is this Zoom call? We're running for another 30 minutes, and we have about a minute or two left on break. Are you a robot? That's up for you to decide. Okay. Are cars hybrid robots? We share the controls, anti-lock braking, for example, controlled by the car. Okay, I see what you're talking about. So you're talking about like, can we make a new class of things, which is basically it has a bunch of robotic systems, but it doesn't operate on its own. Can we say some kind of hybrid robot? That's an interesting idea. Anything that we interact with, right, doesn't I wouldn't call it hybrid in the way that humans interact with it. It also, has sensing units and all that kind of thing. I wouldn't qualify that as a hybrid robot. But like we were talking about before with cars, right, as a big one, there are a lot of automated systems within a car, which in a non-self-driving car doesn't allow the car to really operate on its own. But all those automated systems together do contribute to some kind of robotic technology. Have you seen the Stop and Shop robot? I have not. Do you know when the first robot was made? That I do not know off the top of my head. I do, however, know, what's the guy's name? It's like Joseph Engelberger or something. Is known as the father of modern robotics. That is something I would strongly encourage you to look up, the origin of robots. All right, I'm going to move on with the second half of this talk. And so now, in spirit of the challenge that is a big part of the feature construction thing we're doing here, I want to talk about designing robots. So this is just for you guys and how you should think about designing your own robots. So the first thing I want to talk about is form. There was someone in the Q&A who was talking about robots that are designed to look like people, right? And that's a really big thing. So we generally some kind of bipedal robot, right? They often are designed to look a lot like people, and this is incredibly difficult to do. Uh, Making something that's human designed for the sake of it is rarely done. Most of the time, we make something that's bipedal with arms and a head. It's for research purposes because it's just incredibly difficult. And there are very few tasks that people can do that are easy to replicate in a robotic form. Say, picking something up, a forklift is going to be better at picking something up than a person is, right? So when we make something like a bipedal or humanoid robot, often what we're trying to do is replicate the variety of things a humanoid form can do. So while a forklift can lift things up and put them down, right? Very heavy stuff. Uh, it can't crawl into a tight space, right? It can't jump. These are things humans can do. So if we make a bipedal robot, we want something which can do all of those things, not just one specific thing. So I actually have a video that I'm going to pull up, which showcases how long it's taken us to make very small baby steps in the field of humanoid robotics. Give me 1 second to pull this up. There we go. So this is a clip from Boston Dynamics. They do some of the coolest humanoid robotic work in the industry. And you can see on the left, there is a video from 2009. And on the right, there's a video from 2019. That's 10 years with a whole staff of people working on
space that you'd like to live in.
Yeah, a whole staff of people working on just that topic, right? So even though it's something which we have delved into, it's something which we're constantly trying to figure out and work on. So don't use you never want to use humanoid robotics lightly. It should always be for some kind of purpose, right? One of the things we do for humanoid robotics is anything which is going to be interacting with people, and we don't want people to feel we want people to feel at ease when they're using these kind of robots or operating alongside them. We might try to give it some humanoid features so that people feel a little better about that. There's a robot called Pepper. It's another robot I encourage you guys to look up when you have some time. That is designed to be human in many ways, and it kind of talks like a person. It has fingers, it has head and eyes and mouth, right? And this just makes people feel a lot better interacting with it than if it was just an inhuman block or an arm, right? So like I said before, this particular robot is a manufacturing robot. And like I was saying with the humanoid robots, right? This is replicating some kind of arm. But when they designed this, they said, okay, why make it a human arm, right? A human arm has a lot of limitations. Our wrists, right? That's very limited motion. The elbow is more limited motion. The shoulder is limited motion. Whereas, this has 1, 2, 3, 4, 5, 6 joints that can each rotate close to 360 degrees, right? So that's taking an element of human design and elevating it to better serve the purpose of just being an arm. So the more specific a robotic form takes, the better it can often do any singular task. I'm curious. Raise your hand if you guys have seen Interstellar. I feel like very few people have seen it, but I am curious. Yeah, very, very few people, right? Interstellar, the fun movie and all, but the important bit is this robot here. This is TARS. TARS is a fake robot. It's not real, but it was a very interesting concept where they said, okay, what if we made a robot that looked nothing like a human? What would that look like if we wanted it to do all kinds of things in space? So the filmmakers designed this right here, which is, it looks like a cube, but it has all these different parts that can make it transform into different functions. So you can see it has the walking mode where it takes its two bits and just starts walking. The standing one where it just rests on its two middle things. It rolls as well, so it pushes itself along and rolls on kind of like spokes on a wheel, right? It even had two little bits that came out as arms um, to pick things up, right? So while it needs to do a lot of things which a human can do, right? We can really design this in any way, shape, or form. As you can see, something like this, it may not be quite as versatile as humans, but in many ways, it's probably it can have some whole other application just based on the way they designed the form. Now, we've been talking a lot about terrestrial robots, right? Robots that are land-based, right? But let's be real, robots don't have to be tied even to the ground. Um, this is this is a robot which I'm sure many of you guys have seen before. This is a drone, a quadcopter made by Mavic, right? Very expensive. Well, I, it is expensive, right? But it's actually a lot less expensive than every other robot I've shown you. So the NASA robot is somewhere around what, $2-3 million, right? The arm right here, that's a 50, 60, $70,000 arm. And so yes, this is expensive, but it's also somewhere around $2,000. So this has a remote control that people can use to fly it and take video and all that. But as any flying vehicle, there's a lot of stuff which is automated behind the scenes. So within this, it has a flight controller that controls that can sense what angle it's at. It has control. It has a camera on the front, right, which can help it sense how far away it is from the ground. All this kind of stuff, right? So don't be constrained to just a walking robot or a rolling robot. Robots can fly as well, right? So form is a very important thing when you're trying to figure out what is the robot trying to do and how do I make the best form for that. All right. And the last bit that's very important when you're designing robots are the sensors. So the computing side is something which you don't really have to worry about right now, right? We're more focused on the reasoning behind the things, but it's great to know what kind of sensors are out there and what you can do with them. So I've listed a whole bunch here, and this is somewhere that I would strongly encourage you to research on your own after today. But just to go over a couple, there are sensors that can sense distance. So these are your infrared or your ultrasonic. Ultrasonic send out sound waves, kind of like a bat, in order to detect how far away things are. And so distance is very helpful. For instance, when we're talking about the drone we were just looking at, it needs to know if there's anything right ahead of it so it can avoid that. It needs to know if it's approaching the ground. Depending on the application of it, it might need to know exactly how high it is, right? And these are all things that you can do with that kind of sensor. For 3D imaging, you can use an IR sensor like NASA Valkyrie does in order to create 3D imaging, or you can use a LiDAR sensor. I can't go into exactly how a LiDAR sensor works, but LiDARs are the coolest thing you've never heard of. So that if you were going to look up one thing, look up LiDAR sensors and try to figure out how they work, right? They're very complicated, but much like the image I showed earlier, of the 3D image made from all the little points, LiDAR sensors are incredibly good at creating that kind of thing. I know I haven't talked a whole bunch about the construction side today, but if we wanted to make a robot that went through a building and we attach a LiDAR sensor and the right program, we could map that entire thing and compare it to a 3D model of an existing design and see if it was made up to spec, right? 3D imaging is super cool. Look into that if you would like. So for touch, we talked earlier about the force torque sensor, and that basically it just detects how strong a pressure is being applied in any direction. And that's used often for figuring out how much pressure to apply when you're grasping something. It can also be used to detect nearby if something hits it. So one of the important things that we consider when making collaborative robots is if we have an arm that's going about and there are people moving around, we need the robot to understand when it is near a person and when it has hit a person. So if you have a good collaborative robot, it might bump someone, but as soon as it bumps them, it will stop, right? Because before we had robots working with people, robots had to be kept in big cages so that people couldn't walk around and get hit by a robot that didn't know was there. So touch is very important for things like that as well. A camera is a type of sensor, right? It's just all about getting information from the outside world. So cameras are one of the most commonly used sensors in robotics. Sound is another sensor, right? So this is your microphone. Your microphone is a sound sensor and is useful whenever in situations where you need to detect if there is something that maybe can't be seen but can be heard. If you are using sound, you can determine a lot of things like what kind of environment you're in. For instance, if you are in a city environment, if you just think of what a city sounds like right now, you can determine a lot from just that. If you hear an ambulance, right, you can probably pick out the sound of an ambulance no matter where you are, no matter what you're doing, because it's very distinct, right? And so just like humans use all kinds of sensing in order to figure out the world around them, robots can as well. Then you have your light sensor. So some sensors use light in order to get other information, but just understanding how light or dark it is often useful, depending on your application. So say you're taking a robot that needs to operate in light and day, right? In nighttime and daytime. At some point, you need to know when to switch what it's using for its primary source of imaging. So if it's using a camera during the day, it might need to switch to some kind of night vision at night, light sensor, right? Then you have things like temperature sensor, which is like your thermometer. And for application for that, let's say you were dealing with a robot that needed to operate in intense heat, but also could melt if it gets too intense. So say you're working near a volcano or such, right? You would want to see the temperature long before. You want to know if it's getting too hot long before it actually got somewhere. So these are some sensors. These are some ideas of what they might be used for. And there are way more. There are far more sensors out there. If you were to go and research anything, I would strongly encourage you to research sensors and figure out what you might want in order to design any robotic system. So this is the last 10 minutes that we have today. And so for the cool down activity, I want you to take the design that you did during the warm-up activity and modify it using today's lesson in some way. So consider integrating a new sensor, right? That will either explain how your robot does what it does, or will improve how it does what it does. Consider changing its form to better suit its task, right? Or make a completely new one. and use the sensors that you learned today, use the different forms, use it to design something that is going to be very good at doing whatever you want it to do. Kellyanne, I don't know if you wanted to talk more about the Make It Green Challenge, if there's anyone here that doesn't know about that today. But I wanted to check in just in case.
Thanks, Khalif. You are doing an awesome job. I learned so much today. And beyond, I used to just know why our coffee machine at Autodesk wasn't a robot, but now I've expanded my knowledge. So the design challenge is the Make It Green challenges that we showed yesterday. The one challenge is to think about issues of environmental justice in your neighborhood. So you could maybe integrate this robotic design challenge into that as well, to think about maybe there is a robot that you could design that could address an issue of environmental justice in your neighborhood. On Thursday, we're also going to hear from Thompson Island, Outward Bound, and they're going to talk about real problems that are happening on Thompson Island that they would like to crowdsource solutions to some of these problems by middle school students. So that's you. Khalif, do you think that you could bring a robot out onto an island to solve a problem?
Of course.
So I think that anything that you're doing today could be something that you could build into the larger design challenge as well.
Another thing to keep in mind is, just like when we were talking about robots and automated systems, it's never completely necessary to say, let's throw a robot at it and that will solve all our problems, right? The key is figuring out what are the right tasks for the job. So in your larger designs, as you get more into the design challenge, consider even automating little things, right? So say you were building a house, right? Automate the doors if you'd like, right? If you think that's part of what makes your design shine. It's not always about the whole thing being a robot. Sometimes it's about taking one thing and automating that to better suit its function.
So I know EcoRise on tomorrow's episode is actually going to talk a little bit about living walls. So that could be a place where you could sort of integrate robotics maybe into the system, that, you know, the hydroponic system or like the watering. Khalif probably has better ideas, but that's one.
Oh, who knows? Honestly, the idea is just the tip of the iceberg. Because really, as soon as you get into any one idea, there are so many different ways that you can approach that, from any design angle, but specifically for robotics. You know, take cars, right? Right now, when we think of moving people around a city or a state, uh, often you think of, okay, you know, if everyone had self-driving cars, we could fix all the traffic and everyone could going at speeds, the cars would all talk to each other, right? um, but then there's also, you know, that's one way to approach that, right? The other way is, okay, we can take that same idea and just, if more people use public transportation, there are fewer cars on the road, right? And then you say, okay, that can go one step further. Fewer people need to own cars if people are using systems like Uber, for instance, right? One step further than that, what if Uber was automated? What if you could just call a self-driving car, right? Now you're combining multiple ideas of automation into one. So really, it's never the one idea. You always want to have different ideas and see how can we put these together to best solve whatever problem we're going for. I need some last minute questions. When did the webinar end? So this is actually the end right now. We're doing the cool down activity. Actually, let me quickly show, in case you are in a hurry. I'll pull up the activity again in a second, but I want to show you guys this link here. So we will have recordings of all the sessions that will go live sometime next week, I believe, at this link right here. So if you want to take note of this, this is a great time. So if you weren't able to get on yesterday, we will have the recording live there. Right, I'll just go back to the last slide now. And in the last couple minutes, if you have any questions, now is the time. Can you repeat what you said about not getting on yesterday because it cut out for you? Okay. There is a link. Let me show it again. I don't believe the recordings are up now, but there will be recordings of all sessions, this one and the last one as well, and all future ones will go up at this link later on. If you need a better explanation of just the challenge itself, what's happening throughout this week, there are going to be different webinar sessions this entire week, which I have a schedule I can bring up actually. So I'll do that in a second. And they will each be covering different topics, which will culminate in a design challenge that everyone's invited to participate in. When you can incorporate anything you've learned from any of the talks to create your final design. Present this. This is the schedule for the week, and everything's going at 1. I believe it's the same link that today's Zoom is at. Doesn't look like we have any more questions, but I'll give you guys one more shot. If there's anything you'd like to ask. I will encourage you guys again, look up sensors, look up different types of robots. Think incredibly broad as to what you can use robots for and how can you use automated solutions to create new designs. What material is commonly used in the construction of robots? Currently, a varieties of metals. Generally, for robots, we want things which are very light. So that's your, there is a lot of steel, which is a bit heavier, but your carbon fibers, aluminums, and other light metals, right, are nice for any situation where you have a motor which is not very strong. One of the biggest things to figure out when you're making a robot, when it comes to the strength of it, is how much can any of your motors actually lift. So some of the robots I showed today, say the UR5, the manufacturing arm, right, doesn't actually have a very heavy lift capacity. I believe it can lift somewhere between like 2 and 5 pounds or something, right? It can't lift very heavy things, and that's kind of the trade-off there. So any heaviness in the material is going to drastically change how much weight you can lift. But then you take the Boston Dynamics robot that we showed flipping around, that can lift 10 pounds, and I believe it can lift stuff even heavier. because it's fortified by legs. So it has a whole leg system. It has a better grasping with two arms, right? And that helps it be able to do things that just the one arm could not. That said, the direct answer to your question, most commonly used is probably aluminum and steel. Steel for strength, aluminum for its lightness, and they're both relatively cheap. Right? Titanium. If memory serves me correctly, titanium is expensive. Let me check that. I'm actually not sure. I can't think off the top of my head of any robots I know of that have titanium in them. My knowledge is not the most broad in the world on that topic. Definitely something to research, right? But I would guess titanium's more expensive than you'd want. How much time is left? This is the end. I've done the whole hour at this point. So any time left is just for any questions you guys have. Google and Alexa considered a robot. So this goes back to what we were talking about with the definition of robots being about sensing, computing, and actuating. So the Google Assistant and Alexa, they have a lot of the computing side. If you have one of the units which listens for you, right, that is the microphone is sensing something, right? So you have those two sides, but you don't have the actuation side, right? So if you used Google Assistant or Alexa and then gave it, some way to kind of move around or do something based on what you asked it, right? Then you could call it a robot. But otherwise, it's just a virtual assistant. Smaller robots harder to build than larger robots. Depends on the scale we're talking. If we're talking like really tiny, harder to build, yes, but doesn't. Okay, so if you build a very big robot, like let's say you wanted to build a robot the size of a house, that is easier to build than say something that's microscopic, right? However, there's a reason the microscopic robots are something which has been researched and done, and the really big one is something which people have done it, but not really, right? They generally can't move very fast or do very much. They're just generally less useful in the larger scales. That said, it's being done and will keep happening, but that's kind of a difficult question to ask or to answer overall. Is titanium light and strong? Honestly, I don't know the specifics of titanium itself. I would suggest you research that one. Can we leave when we need to do something? You are free to leave whenever we are done for the day. Is a video game sensor a robot? I don't know what you mean by a video game sensor. Can you clarify that? If you hook it up to special light bulbs, you can tell your Alexa to turn them on. Okay, that's a good point. So if you take a Google Assistant or Alexa, and then you have other systems like smart light bulbs or other smart house features that can change the temperature in your house or start your coffee maker or do your laundry, right? That kind of thing. Then yeah, that's exactly what I was talking about when it's about taking that one thing on its own may not be a robot, but if you attach other automated systems, now you've made something which essentially is a robot. Okay. So you're talking about the question about a video game sensor robot. You're talking about the game controller itself, like the video game knowing the controller is plugged in, or more the controller itself, right? Um, Either way, they're both missing one element, right? So the if you're talking about the video game itself and the fact that it can sense what the controller is, the input there, you're doing all the actuating, you're moving everything, you're pressing the buttons, right? Uh, it's not doing that. Even if you think about it like, oh, the vibration side of things, if you do something in a game and then it starts to vibrate, you could say, okay, it's sensing something from the game, blah blah blah. But even then, it's dubious to call that a robot, right? That's just another version of automation in some side. So a lot of things which are essentially just computer code. Everything in a computer is automating something to some level, but it needs that extra step before we call it a robotic system. And sometimes if they have a bunch of things, which yes, some things are actuating, some things are sensing, some things are moving. If it all doesn't all come together into one specific purpose, I wouldn't call it a robot, right? Say for instance, if you put Alexa on a car and Alexa could run the car whenever it's talking, technically you've made something which is sensing, is computing, and is actuating. But the actuation doesn't have anything to do with the other two parts. So you can't really call it a robot just because it can do those things if they're not really connected. If they are connected, right, then that's a whole different story. If you can tell Alexa, okay, drive me to the store, and it does that, robot, right? If you tell Alexa, I don't know, drive forward, and it drives forward, even that is technically, doing something robotic. But in the way that we talk to Alexa about, you know, how's the weather today, stuff like that, set a timer for me. It's definitely automated, but it's not robotic unless it is actually doing the moving thing. But like you said before, if you attach it to something like a smart light, then you have your actuation. It's turning lights on, right? That makes it a robot. All right. So I think what I'm supposed to do for the cooldown activity. Um, Let me reshare that bit. There we go. That's just taking the design that we talked about in the warm-up activity and modified in some way using the stuff we learned today. Say, take a sensor that you learned about and integrate that into your design uh, to make it better, uh, changing its form so that it's more suited to its task. So if you're doing something that's lifting something, maybe originally you had it being a whole human, but now you're like, you know what? It doesn't need to do that. It can just be a lifting platform on wheels, right? Or make a completely new one, right? But the idea here is I want you to be thinking about robotic systems when you get to the design challenge later in the week. If a robot senses something virtual and acts on it, is it a robot? Um, Generally, we don't say so because we most of the time are talking about things in the real world that we're sensing, right? Um, but even then, we're starting to get a little nitpicky about the word robot, and we don't actually need to, right? We don't need to always identify robot versus not robot. Um, it's interesting to think about to some extent, but after a while, you know, where you start to figure out exactly what does and doesn't fit, you have to ask, okay, at what point am I asking a question that doesn't help me figure something out moving forward, right? Do we build a robot or just draw and write the design? This is just writing it, right? Just design it, sketch it if you'd like, write it down. We're not actually going to be building a robot in this particular lesson. Is a keyboard a robot? What are the limits of a robot? And are birds robots? I'll answer the last one first. Birds are not robots, unless they are. We don't know. Some say the government created birds to spy on us. I would say no. There are robots that are shaped like birds, though. I remember a particular robot that was not a bird, but a dragonfly, but they actually had made something that had dragonfly-like wings that could fly like one. It's super cool. Limits of a robot, that's just based on what you design it to do, really. Did you know there was a bee robot? I did not know there was a bee robot. Smaller than a penny. That's incredible. There are incredible things done with very, very small robots. I believe there was one made that was literally microscopic. Is a keyboard a robot? Probably not. Depending, I mean, you could make a keyboard a robot, but you are doing the pressing of the buttons. The keyboard itself doesn't really do any actuating, right? It's not moving anything. It's not physically representing itself in some kind of motion way, right? Saw it on game theory. Oh, game theory is great. Right. Okay. Oh wow. I guess a lot of you guys like game theory. Is a TV a robot? That's another one that depends on the TV. There are TVs. There are robots that have TVs, right? There are TVs that have automated systems, but your standard TV, you turn on, you turn off, right? It's not doing anything on otherwise. Right? It's a clap-on light a robot? A clap-on light. Man, do people actually have those? I remember the ads for those like way back when. You know, the clap on, clap off. Very fun. But no, you're turning it on and off. You're doing the I guess it's sensing. That's not true. I lied. It is sensing it. It is turning it on and off. There is some level of computing happening there, but it's honestly because just like with everything else, and we're starting to get very nitpicky here. Just like with kind of automatic doors, yes, you could call it a robotic system if you'd like. The computing element of it is kind of small, right? So it is automated, definitely is automated. Is it a robot? That's a judgment call. A lot of people would say no. Okay, it looks like most of the questions here are again about like what isn't a robot. But I think that's my time today. If you would like, feel free to to design robots in your spare time using kind of elements from today, and think of these things moving forward as we get into other elements of this week. So with that, I'll see you guys. It was great having you.